Hello, colleagues. Today, let me welcome Dhruv. Dhruv Shah is a final year PhD candidate in EECS at UC Berkeley, where he is advanced by Sergey Levine. His research spans the fields of machine learning and robotics, with general goal of enabling real-world robotic systems perceiving and acting in the wild. His research is supported by the Berkeley Fellowship for Graduate Study and was nominated for the Best System Paper Award at RSS 2022. Earlier, he graduated with honors from IIT Bombay, where he received the Undergraduate Research Award and the Institute Academic Prize. And today we are going to listen to his lecture. Dhruv?
All right, great. If my audio cuts out at any point, let me know. My microphone has been known to be buggy. But great, I'll get started. If you have any questions, I'll try to have two checkpoints in the middle of the talk, and then plenty of time at the end of the talk, so you could just I'll open the floor and we can do questions then. Great. So I'll be talking about a lot of my PhD work, which has been in learning visual navigation policies for environments indoors, outdoors, and places you haven't been before. But I'll try to kind of make this talk a little bit more general in terms of how these ideas can be applied to any robotics problem. And I'll particularly focus on what the value of real-world data collection is, as opposed to training from simulation versus training from any other sources. Great, let me get started. So I want to start off with a shout out to some of my favorite and objectively impressive robotic systems from the last few years. And I hopefully don't need to convince anyone here that learning-based systems are cool and have achieved some immense feats. And they really challenge what we think is possible. These are all robots running learned neural networks, most of them on board, with onboard sensing, low environment instrumentation, and solving challenging tasks in the wild. And broadly, these fall under two general buckets. On the left, we have some really impressive agile drone flight in unseen forest-like environments. And through kind of the hood, the key to getting this to work is large-scale simulation training in a game engine. So you design a game engine where the environment is very similar to what the real-world test environment is going to be like. And while this has turned out to be a very good recipe for many applications, modeling every environment in sim may be challenging. And while sim to real transfer kind of works for modalities like depth and proprioception that are easy to simulate, it can be arbitrarily hard for other modalities like RGB or LiDAR or so on. On the right, we have methods that rely on large-scale real-world training with hundreds, if not thousands of hours of data collection on fleets of robots. And I have one example of manipulation robots here, but this stands in place for a lot of other real-world robot results. And this is great because policies trained on your robot tend to work very well for your own robot and your own tasks. But doing this for every robot and every task is outright impractical. And even when done right, the policies can be very brittle because they're trained on very narrow domain data sets. And all of this boils down to the challenges with real-world robot learning. Well, the real world is hard to simulate, as you would expect, but also collecting data is a very high barrier for entry. Every time we need to collect data, there's a lot of cost associated with it, and it might outright be infeasible for systems like this one, which is a narrow bound from MIT, where the battery life only lasts for about 4 or 5 minutes. So you cannot collect hundreds of hours of real-world data. And even when done right, if you only collect data from your own robot, your learned policies will be fragile to perturbations in perception and dynamics. But it doesn't need to be. At first glance, our robots are very different. So you're doing different tasks in different environments. If you're a manipulation researcher, you may have one of a few different robotic arms, or even your own arm. Similarly, if you're a mobility researcher, you may have one of a few different mobile platforms with different capabilities. Some can walk, some can fly, and so on. But if you zoom out enough, and the roboticists in the crowd may be unhappy, but from a learning perspective, most of the tasks are actually quite similar. It may not be obvious between the top and the bottom, but within the manipulation or within the mobile robots, all of them need to parse visual observations, plan to the goal, execute some actions, avoid collisions, and so on. And I believe that the embodiment gap between a new robot and existing real robots that perceive real images and control real dynamics of the robot, so the real to real embodiment gap, might be much smaller than sim to real embodiment gap, which is what we struggle with when we train in simulation. And especially when this comes to modalities that may be hard to simulate, like getting photorealistic RGB or light. So in this talk, I'm going to talk about a different way of thinking about real-world robot learning, where we focus on pre-training policies from robot data across different embodiments. We take a bunch of different real-world robots, and I'll go into the details of the task in a minute. And then we train a large model, which is what we call GNM, or General Navigation Model. And this large model can be kind of seen as the pre-trained model to use. Our objective is to train something that could be a good starting point and serve as a plug-and-play default policy, something that you can download off of the internet, and then without much effort, get simple behaviors out of it. And to solve the task that you really care about, you would fine-tune this model with a small amount of data, with a new sensing modality or a new robot embodiment, or different objectives like reinforcement learning and so on. And so whatever model you design should be able to do this efficiently. Before we go any further, I want to touch upon the choice of the phrase, the robot foundation model. We use this word a lot, and we all mean different things. So I want to describe a specific interpretation of what I mean by a robot foundation model, and then we can revisit the definition at the end if people have other versions of it. So I would define a robot foundation model as a model that, once trained, can be used zero-shot in a completely different setting. So in this case, that would be different robots. But it could also be adapted to a downstream task of choice. So different objectives, different ways of specifying the goal, different behaviors, and so on. I just want to put this here so we're all on the same page, and then we can debate this later. And this talk will kind of be about our work towards how you can build such a foundation model for the task of navigation. As a quick overview of my talk, I'll first talk about what it takes to train the cross-embodiment policy backbone, which is what I talked about. And I will call this the foundation model for navigation. And we will show that how this can be used for generalizing in zero-shot to a wide range of environments, different embodiments, and so on. Next, I'll talk about how such a policy can serve as a starting point for a range of downstream applications by fine-tuning or adapting it with different kinds of sensing modalities and objectives. In particular, I'll show how this can serve as a starting point for training policies for off-road racing, off-road or indoor racing, where we want to see if learned policies can match or exceed human performance. And lastly, I'll talk about how this can serve as a starting point for training socially compliant navigation policies and for autonomous data collection with human-robot interaction. I'll try to make a case for why these kinds of applications necessitate learning from real-world data, and it will be difficult to achieve purely from simulation or passive data. So before we start, let me describe the general setup for everything in this talk. So you go to an environment, in this case, let's say an outdoor environment that the robot has not seen before. And this could be outdoors, on-road, off-road, or indoors in an apartment building or an office or whatever. You have a mobile robot with a small computer on board to run learned policies. And the robot is equipped with a forward-facing RGB camera. You have access to simple proprioception like local odometry, but you don't have access to anything else in terms of global localization. And given these inputs and some goal, which can be specified in a variety of ways, like an image or a language description or a trajectory to follow, your policy must process all of these information to spit out actions that the robot will execute. And I want to put a disclaimer up front that these assumptions, and hence all the methods that I'll speak of, are not prescriptive in any way. In no way am I suggesting that the best way to solve the navigation task or any other task is by using only egocentric images, and you should not use depth or LiDAR or so on. If you have better sensors or privileged information and localization, by all means, you should design methods that use it. But we'll use this as a setup that allows us to break down the problem and utilize a bunch of existing real-world data, since most of them have visual sensors, and study how things scale up and how we can use them. Great. So let's get started with the first chunk, which will be about half of the top, which is the pre-training step for the policy development. Broadly speaking, there are three sets of challenges towards this goal. As in every machine learning problem, we need to figure out what algorithms we're going to use to train the models. We need to figure out where the data comes from, which is particularly challenging because this is active robot data. And of course, we need to design architectures or models that are not only able to absorb all of the knowledge in the data, but they can also be adapted and scaled flexibly for increasing data sizes and for downstream applications. For the algorithm, they use a self-supervised objective that uses trajectory level labels that are readily available in the training data. So we use the temporal distance between frames. So if you think of this as a video, given a start frame and an end frame, you want to predict how far they are in number of frames. And then a set of suboptimal actions, which is your policy function, that can be taken by the robot to reach the goal. And we train all of these models with goal condition behavior cloning, but I'll touch upon how this can be modified to use reinforcement learning, in particular offline reinforcement learning. On the data front, rather than collecting our own data, since we want to do this across different embodiments and across scales, we aggregated a large cross-embodiment data set sourced over 10 different robots and research groups, which were collected on robots with different speeds, sizes, capabilities, and different action spaces. And also because these were collected physically by people in different locations, we get to sample a lot of different environments around different places in the world. And for the model, we proposed a new high-capacity transformer-based backbone that uses past observations and goals encoded as visual tokens to predict the targets. And we also use a fusion process of our actions to represent the action distribution. I'll get into the implementation details of these in a bit, and we can take more questions. So before we get into the model itself, we need the data. Rather than training an individual policy for each of the robots like you would typically do for real-world learning, we can instead combine all of these data sets into a large heterogeneous data set, and let's call this kind of the data set of choice. And then we will try to train a whole policy on this data set, even though the data set has a mixture of different behaviors. To talk about the architecture, we're going to start with a typical goal condition navigation model. So you can imagine this to be any goal condition model where you have a state, which is your observations. You have your observations. You have the goal that you intend to go to. You tokenize them using your favorite convolutions, and then you have a few fully connected layers to predict your targets, which in this case are distances and actions. And these kind of models have been used for a variety of tasks, not only navigation, but manipulation and even non-robotic tasks. So we're going to make two changes to adapt a typical goal condition model so that it can be used with diverse data sets and different sizes and so on. First, we'll abstract away the low-level controllers of each robot and make predictions in some sort of a normalized action space. So the outputs of the model, which is the estimates of temporal distance and future waypoints, they're scaled by a robot-specific factor, such as its speed or size, and abstracting away the variance of the different controllers across robots. And further, we are going to condition the model on a sequence of past observations from the robot's viewpoint, which gives us a mechanism to provide an embodiment context to the model, which can be thought of as an implicit system identification stage. So the model knows what robot is driving, what its capabilities are, and so on. And we find these two simple modifications essential for training on data sets that have such a large amount of diversity. Next, we looked into how we can scale up these models so that they can actually be trained on hundreds of hours of robot data, all collected by different people across different labs. So while this is still a small number of parameters by the scale of a generative model, it's still quite large for active robot policies that are running on the robot. So to scale this up, we're going to make changes on two different axes. The first, the simple thing to do, which is scaling up the network capacity in a somewhat modular way, so we have more tunable parameters to play with. And second, scaling up the expressiveness of the model for generating more diverse behaviors. So just as before, for any goal condition policy, let's say you have a sequence of past observations and you have a goal observation that you want to get to. We would tokenize them using some large convolutions and then pass them through a fairly large multi-headed attention block over the token space to predict the future distances in action. The resulting model, which we call VINT, or the Visual Navigation Transformer, it uses large visual encoders and a transformer architecture to learn a cross-robot goal condition policy. VINT contains about 30 million trainable parameters, which is about 1 to 2 orders of magnitude larger than typical models people run on the robots. Again, this is quite small by the standards of LLMs and VLMs of today, but for something that's trained from scratch only on robot data, this is actually quite a large model. And we can do a few tricks to get this to work in real time and get real-time inference on board. Secondly, to go kind of beyond just naively making your models larger, which you can now do, a big thing which we worked on is how do we make the action distribution more representative. So to do this, we take a context vector from the attention block just as before, and then we condition the diffusion process over past observations and optionally over the goal as well. So in this case, if the goal is not specified, the model predicts unconditional samples from the diffusion model to predict all possible futures. But when a goal is specified, the model predicts samples that go to the goal. So this allows us to not only make the model capacity larger, but actually have more expressiveness baked into the model so you can capture more complex behaviors in the world. And the really nice thing about training across data sets on a lot of these, a lot of the diversity that I touched on, is that you get robustness for free. So for instance, we found that the trained model is robust to dynamical degradation, such as tire damage. So we had a piece of wood here lodged in the tire, and this damage affects the dynamics of the robot, as you can imagine. Actions corresponding to following a straight line using an open loop controller lead to a collision because the model doesn't know that it has a problem. But you find that our learn policy, because it has been trained on a lot of different robots and a lot of different environments, it has kind of learned some sort of a robustness to changes in the robot's dynamics and can successfully reach the goal despite these challenges. We also see similar robustness on the perception side, where we test the robustness to camera viewpoints. So shown here is 3 different mounting points for the camera, and while the perturbation seems subtle, if you kind of look at the encircled areas, the images are actually quite different. And if you only train a policy from a single viewpoint, it would completely break if you change the height of the camera. To test this, we collected a demo kind of trajectory, a graph with a fixed camera viewpoint, and deployed it on the robot with perturbed viewpoints. And as you can tell, the policy can reach it despite different heights, which shows that you can change the viewpoints during deployment. And kind of the extreme case of changing viewpoints is that we show that it can generalize to entirely new embodiments, which in this case is a quad rotor, which is restricted to navigate in a 2D plane. So it's kind of like driving in a 2D, driving a quad rotor on a 2D space. And using just RGB images shown on the bottom left, the policy generalizes to a completely new embodiment, despite never having seen data from any aerial robot during training. And there's also a lot of shake in the vertical space, which it needs to be robust to. And jumping onto some more videos, here's the same model running in real time on a Go on quadruped. We did a demo at the Coral conference a month and a half ago. And this is a completely new environment the robot has never been on. We just put the policy on a quadruped time, and it asks us to the other end of the hallway, and white and so on. This is particularly interesting because none of the training data actually have any humans. I don't know if it's working very well because usually when I'm sharing the screen, the video is over in but this is the one video and it's moved out of that. We also showed that you can run this model indoors and outdoors, like controlling quadruped, which was never during the training data, but it's doing condition navigation outdoors. And here's a sampling of the same model, the same checkpoint without any fine-tuning or additional data collection. This is the exact same model being run on 4 different robots in very different environments and solving the same task across robots, across environments, across sensors. Trying to quantify these performance improvements, we compared our models trained on cross-embodiment data, so data coming from different robots, with the best single robot model available. So roughly what this orange bar looks like is trying to gauge what is the best performance you can get using data from your own robot and training the best policy you can find. Try not to compare the charts across the different robots because they're all different sizes and they move at different speeds. So it's not particularly well normalized. And so keeping the architecture the same, but then training the same model now on data across different embodiments which is the GNM baseline here, which is a small model of the same size but trained on more data. We see that, well, we can already match each robot at its own performance. There's a small degradation in some robots, but roughly speaking, what this gets at is that there is capacity in a single model to control multiple robots without affecting performance. And then when we go to the larger model, which is the WINT model, which is about 3 times larger, we have not only can we perform every single client, every single robot, but we can also additionally get a lot of positive transfer, which is data on other robots actually helps performance on your own robot. Not only does it help your own robots, it also has a lot of these things you got results where it helps other robots. Most notably, this suggests that training data from other robots and other apps is generally not a bad idea. It will not hurt your performance, but it will also help with and kind of as a note, broad zero generalization. It's been about a year and a half since we released the model. GitHub, when it releases code, deployment, checkpoints, everything. And a number of people have tried zero-shot deployment models. Is the sound bad? Is it? I got a chat message from someone saying the sound is bad.
The problem is that the sound is flipping and cutting, and so the last, I guess, 5 minutes.
Okay, can you hear me?
Yeah, very.
Yeah,
Sparsely.
Okay. Is it still choppy?
Yeah. No, it's better now. Thank you. Could you please, yes, say one sentence?
Okay, great. Yeah, so since we put these models out, a number of people have reached out to us and shared videos of these policies running on their own robots in different places around the world. So this is literally somebody downloading the public code in Checkpoint and deploying it on their robot in Estonia or Princeton or Finland. And the model continues to perform somewhat reasonably, for instance, here, avoiding obstacles on the right, or this is on the bottom, there is the drone that's flying around the hallway. And all of this is completely zero shot without downloading any new data, without fine-tuning the model and so on. So in some sense, this is kind of the real unicorn test for robot models where you're testing it in a completely held out environment. And while we're in the subject of generalization and robustness, I briefly want to touch upon why I think this works and why cross-embodiment training should work. It's not magic. It's not going to work on everything that you drop. But in a sense, it's not very different from how domain randomization has been working for the last 5 to 6 years, where in simulation, you randomize the heck out of every distractor variable of your simulator to make the models robust and to make them generalize better. By sourcing real-world data from different robots, different labs, different cities, and so on, we are implicitly randomizing over all sorts of distractor variables, such as camera intrinsics, camera extrinsics, positioning, different speeds of the robots, turning radiuses, lighting conditions, and so on. And during inference, the model is conditioned on an implicit notion of a sysid, or the embodiment context. So it knows the important stuff while ignoring distractors that are not as important. And in some sense, we are trying to learn this average or median behavior across all the robots, which would mean conservative behavior that stays within the support of all the data sets. So when it's applied on a new robot, it's just going to act conservatively, not get into collisions, but still not fail completely. Moving beyond generalization, a key desire in pre-training such a policy is to be able to fine-tune it efficiently for downstream tasks. So here we're comparing the performance on a completely held out task. And since all of these models were trained in real using real data, we thought, well, what's the most held out difficult domain you can get, which is not the real world? So we went to a simulator, we went to Carla, and we set up a task where the robot needs to drive from point A to point B in a city while staying in the lane. So let's say what you see in the orange bar is a model that is trained completely from scratch using a few hours of Carla data to stay in the lane and reach the goal. And a common way to kind of pre-train this or to initialize this policy would be to use a visual representation, let's say an Emergent policy or a policy pre-trained with a self-supervised objective like Sinclair or DC1, which is a robot-specific ResNet, which can be used to initialize these representations. And unsurprisingly, training from scratch is not really sufficient to learn the task, but initializing with pre-trained visual features and fine-tuning the entire model doesn't do that much better either. If you tried GNM, which is a smaller model but still trained across different robotic tasks, we see some performance improvement, and more so with WINT, which is this larger model. And we significantly outperform all the other ways of pre-training. And a hypothesis for why this might work better is to do with policy level pre-training versus visual pre-training. So if you think of the other baselines here, we're only pre-training the visual encoders, versus GNM and WINT are talking about pre-training entire policies. And the hypothesis for this is that policy pre-training captures better features that are task relevant. So since they're conditioned in the control objective, let's say they're more predictive of collisions, or they're more predictive of the affordances, like which patch of ground is more traversable than the other. And rather than kind of just general visual features, which have different invariances that are defined for them. And we also see this when you vary the amount of fine-tuning data. So we find that pre-training with pre-trained WINT out of the box, or with only 5% of on-task data, already outperforms a policy that is trained from scratch with over 20 times that much data. And at just about 40% of fine-tuning data, or close to an hour of on-task data, the performance saturates the highest value. So what this stands to show is you could download the policy, get about an hour of data in your training environment, and you would get state-of-the-art policies without having to collect hundreds of hours of data yourself. I'll touch upon one last thing before we can pause for some questions. We explored a lot of cool possibilities enabled by a transformer architecture, but I want to discuss the one that I'm most excited about. So in the language modeling community, which has been using transformers for a while now, a very successful use case of transformers has been by prompting them to steer the outputs, which is what we all do. So the idea of prompt tuning gained popularity, where a learned prompt can be used to efficiently adapt the model without fine-tuning the whole model end-to-end. And we find that WINT, even though it's very small, it supports this notion of prompt tuning. So concretely, what this looks like is we utilize the fact that the transformer operates in this token space. So one token contains goal information. So if you remove the goal image head, but you keep the token, and then you map that token using a different encoder from a goal modality such as language, or using position from something else, we can completely throw away the goal image attending properties of the transformer, but then still have everything else work the same. And the rest of the model already has pre-trained weights, so it already stores some sort of behavior agnostic to the goal. Sorry. So yeah, you throw away your goal image encoder, and this allows us to kind of quickly adapt the model to new tasks and new goal modalities with a small amount of data. Since you're only fine-tuning about 2 to 4% of the parameters of the model, using a small amount of data, you can now fine-tune for entirely new goal modality, which can get you, let's say, navigating to GPS positions or some sort of routing commands. And you can still retain like basic information, which is your pre-training, and then you can learn tricks by fine-tuning. I was going to switch to the next part, but it's been a long pause. So if people have questions, we can take some questions now or save them all for the end, as you prefer.
I have a small question about this goal image. How important the similarity of this goal image to the initial observation is? Because probably, for example, this goal image can be, for example, for the different room with different colors of the wall and so on. It probably gives us nothing.
Yeah, that's a great observation. So the way I think of this is, if the goal image, in the simplest case, right? If this was kind of trying to do correspondence between two images, if the goal image has any overlap with the original image, then this would kind of be like a learned correspondence detector, which says, oh, the goal image is somewhere to the right and front. So this is the action I should take. And if the goal image is not informative at all, then this would learn an exploration policy, which is, let's say, well, I don't know where the goal is, so the best thing I can do is take random actions that take me to a more informative part of the state space. And that is the behavior we actually observe. So if I'm standing, if you're standing in a hallway and I give you an image of something that's not in the building, there's not a lot you can do except learn priors such as, oh, I see the hallway. I should just take the hallway because it's most likely to get information. So because this is trained on real data, in the real data, if I give you a completely irrelevant goal image, the best you can actually do is continue exploring till the goal image becomes visible. And that is the kind of behavior I see here. This is suboptimal because if you had a vector, like a goal vector has a lot more information than just a goal image, because even if it's not reachable, you know which direction to explore. But yeah, those are the trade-offs.
Okay. Thank you.
Yes, Kasha, go ahead.
Hi, Dhruv. Very interesting work. Guess my question is about, like limitation of this to what classes of robotics problem do you think this generalization happen? For example, I'm thinking if we have a contact-rich problem, like manipulation with varying end effectors, like let's say different suction sizes. I couldn't help but to think we have to provide some model of the end effector or some model of the contact-rich sort of physics so that it can generalize over cases like that. I'm just curious about your thoughts on that.
Yeah, that's a great point. I think one clarification, even though I've been calling these things policies, I think the right way to think of this is these are not exactly control policies. They're kind of like mid-level planners. So if you think of the job of a planner, it doesn't operate at the level of the dynamical rich control things. It operates at a slightly higher level. So the way I would think of this is at the start, when I tried to define the abstraction, what we did is we came up with a notion of a shared action space that is true across all of the robots. And you should be, you should be able to define that. Now, if let's say the task we're talking about is dexterous in-hand manipulation, it can be very hard to define that abstraction because different hands and different morphologies will have different ways they do this. So I would think unless we can come up with that sort of shared action space, and then for each robot, you can have something that decodes this shared action space to their own action space. So if you were talking about non-dexterous manipulation, let's say pick and place, opening things, a good abstraction can again be waypoints. So you can plan the space of waypoints, and then you have your own inverse kinematics model for each arm, which goes from waypoints to joint angles, and that could still work. But if you cannot define that sort of abstraction, then it's very hard to share data across the robots.
Thank you.
Okay, great. We'll move on to the next part, and then we'll have more time for questions at the end if other people have questions. Great. Yeah. So far, we've talked about how you can train this average case model by pre-training it on different robot data sets, and that's great because it gives me some out of the box properties. But then a natural question that comes up for any roboticist that has their own robot that they really like a lot is, why should I care for average case behavior when my own robot is very capable? So for instance, if I have a robot that can fly in 6-staff or drive really, really fast and pick up dirt and drift into the corners and do cool stunts, why should I use an average case conservative policy? The goal with B&M so far was to get a policy that can do a large number of things robustly and kind of serve as a pre-training step. But eventually, all you care about is one thing, which is doing something really, really impressive with your own robot. So how do you go about this? We chose this task of high-speed navigation, which is challenging, kind of similar to the video you saw on the last frame. And people have looked at this high-speed racing in offer environments in a lot of different ways. I'll spare you the time of doing a whole related work section and summarize the key challenges that make up the problem. Getting accurate localization is very, very hard at high speeds. This, for instance, is what the localization looks like for my own robot over 2 consecutive laps. And where global estimates like GPS don't make any sense, but also local estimates are breaking because your wheels start spinning fast and so on. If you're relying on completely local observations like vision for localization, that's also very challenging because ego RGB images at high speeds are prone to motion blur and poor exposure handling. Like most of your frames are just going to be completely whitewashed if you're doing them indoors or when you're facing the sun. And that kind of makes learning from pixels hard as well. And at the same time, a fast policy that has to handle dynamical effects like sliding on slick surfaces. Like in this case, I don't know if it's going to play again, but the robot kind of loses its back end because it slips when it's trying to make this turn. And all of this is to say that if you try learning this from scratch, it would be really, really challenging, much more so than training slower policies. So we clearly don't want to learn from scratch in the real world. And the pre-trained policies I've rambled on for the last 30 minutes or so are not that great either. So then here's a recipe for training what I would call a specialist robot policy that can be very good for a specific task that you care about. But then we can also leverage some of the robustness and generalization qualities from. So first stage, we'll kind of do the same thing we did before, which is we'll try to have this general policy pre-training, which will learn to drive slow and avoid collisions. And that would be the starting point. And then we'll figure out a way to do practicing and online improvement in the real world so you can start exploring parts of your state space and optimize an objective that you care about. So in the first stage, we use, instead of, we could use BC like we did before, but in this case, we use offline reinforcement learning applied to an existing kind of navigation data set and navigation model like we talked about before. But since this is done using data from a bunch of different robots and other robots, these are just general features, not necessarily really good for the task of your own robot. And at the second stage, what we'll try to do then is we'll try to learn a driving policy in in some type of environment. This is, let's say, an indoor environment. We also do this outdoors, where we set up an online reinforcement learning objective to solve the task and get better over time. I won't get too much into the details. If anyone's interested, we can revisit it at the end, and I'll just show you some videos of how this works, and we can talk over it. So when you start, this is kind of equivalent to just taking the GNM policy, putting it on a completely different robot in a completely different environment, and asking it to go fast in a loop. And the policy at the start, it's kind of bad. It knows how to drive slowly, but whenever it tries to go fast, it just ends up hitting into the walls, and yeah, it just ends up hitting the walls and goes all over the place. About 10 to 15 minutes in, we see that the robot has a much better sense of the embodiment. It learns that it needs to limit speeds when it's following hallways, but it also starts figuring out that in the corners it can go a little bit fast, and it'll try to take a sharp turn in the corners. And at about 25 minutes of real-world experience, it has started, mastering what the environment is. So because this is fine-tuned in a single environment, this is the equivalent of overfitting your policy to work really well in just one environment, and that's what it does. So in this case, this is what the onboard footage looks like when you put a GoPro on the robot. It takes sharp turns into the corners. It tries to go really, really fast. And we started keeping track of the lap times. So we define what a circuit around the floor is. And we found that over practicing, what you see on the top right is that the lap times get faster and faster. And at some point, they actually beat the best human lap that we can do. We can also do the same thing outdoors. In this case, all the motion blur you see is because the robot was going really fast and it lost connectivity with me running behind it. And yeah, this is like I kind of shared in the past. A lot of this is happening from egocentric first-person video, which looks like this. That there's a lot of shake, there's a lot of motion blur, and the policy has to learn all of these things entirely from scratch from its images. And yeah, kind of revisiting the same pre-training question from before. So let's say you wanted to train this policy entirely from scratch. It's very hard to just do it from 10 to 20 minutes of data. So let's say you start with an ImageNet pre-trained visual encoder, and then you want to fine-tune this encoder online, and you measure what lap time it takes to do this. And this lap time is in seconds, so lower is better. Naturally, as you would expect, trying to pre-train these visual features with better objectives, which may be more robot specific, like VC1, or something that's more specific to videos like Dino, it tends to be a better prior. But neither of these are actually able to match what we would call a good performance, which is a state-based baseline. I would actually kind of expect some of these vision-based models to approach a state-based baseline, because at the very least, they should be able to have some correspondence between states. They want to be predictive of states, but they were still about 50% off. And we find that our system, pre-trained with the kind of VNF features that I talked about, and improving online, can easily match and even beat both the state-based baselines as well as matching human performance. And this again kind of suggests that pre-training is doing a lot more than just extracting good visual features. It's trying to learn something that's more predictive of control. And on the qualitative side, we also saw some interesting behaviors emerge from the learned policies. For instance, despite the objective only asking for minimizing lap times, we found that the robot learns the concept of a racing line, which is visualized here from one of the simulation experiments, where the robot kind of slows down going into a corner, takes the path of least jerk, and and exits smoothly. This is the kind of stuff that you bake in as inductive biases when you try to make models for racing. So it was really cool to see that in a model-free setting, this was an emergent behavior. We also find that the robot has learned taking kind of high-speed turns on slick surfaces by drifting into the corners. I don't know why my video is not playing, but it's kind of, it's another behavior that it's learned. And lastly, we find that the robot also learns interesting sign preferences, like when it needs to go really fast towards the goal, it figures out that sticking to the road or a pavement is much faster than going into the grass and coming back, and so on. Anyway, and for the last kind of 10 or so minutes of the talk, I'll try to go into another application that you can enable with starting with GNM as a starting point, which is trying to learn with humans in the loop. So fairly simple setup. You have a robot that is driving around a building. Let's say people are doing whatever they're doing, and there's a robot which is trying to execute some tasks, which could look like an inspection task. And you want the robot to not interfere with the humans, definitely not colliding with the humans, but also not blocking or obstructing humans, and generally being compliant. An important thing to note, especially since all of you here kind of work in the AV space, is there's a very large range of how much human modeling you can do. So there's a lot of human coexisting with robots that you cannot fully ignore. The ideal case scenario would be that the robot learns to act in ways that make the human not get annoyed and do the intended task, but also the humans will make inference about the robot's behavior and plan around it in a multi-agent optimization setting. I'm going to ignore these higher-order effects and just focus on the base task, which is you don't want to annoy the humans, and you have a starting policy that you're starting with. How do you make it more compliant? By using end-to-end learning. The robot, as usual, will have an RGB camera and some sort of a map of the environment, and we'll start with that. I want to touch a little bit on the notion of why we actually need real-world data. So a lot of work in this space has been learning from simulation or learning from other sources. And social psychologists have even developed kind of human models for crowd behaviors for many decades now. So many kind of one of the classic models here, which is the social force model, that breaks down. It starts breaking down when you consider that humans and robots are kind of different agents, and they don't have the same models. They have their own kind of rational decision-making agency. People have also tried collecting their own data of human-human interaction and using them to build such models for robots, like this work for George Mason, where they attach sensors to a helmet of a human, and then when the humans are walking in crowds, they collected data about the human-human interactions, and they use that to train human-robot interactions. But it's also quite well known from social psychology that this may not be enough. To quote a prominent researcher in the space, they were studying how much eye contact humans make with other humans versus other robots that are navigating in a space. And they find that the degree to which humans interacted with the other agents, or the degree to which they followed their gaze with other agents, depends a lot on whether the other agent is perceived to have a mind and making its own behaviors. So it not only depends on the fact that a human and a robot look differently, but it also depends on the fact that they act differently. So not only is modeling human behavior challenging in its own right, there is a fundamental dichotomy that human-robot interactions are fundamentally different from human-human interactions and human-robot interactions. So even if you can simulate a lot of robot-robot interactions or capture a lot of human-human interactions, it's inevitable to collect human-robot data and then try to learn something from this joint interactions itself. So that's what we're going to do. We're going to start with a pre-trained model, and we're going to learn from human-robot interactions on the fly in a continual learning setting. So to train our control policy, we're going to add a couple of new terms to the original navigation objective. So let's say JNav is some summary of the objective, pre-training objective that I talked about before, which talks about just learning the base policy. Now, if the robot did not exist, the pedestrian would comfortably walk on the intended trajectory, which is this dark blue line. Because of the robot's plan, the pedestrian has to now change their path depending on the robot's, because the robot is going to do something. So the first objective we'll penalize is this counterfactual perturbation objective, which is, had the robot not existed, where would the human have gone? So you train a predictive model that predicts where the human would have gone without the robot, and then where the human went with the robot, and then penalize these so that it's small. And the other objective is for not violating the pedestrian's personal space, so that the robot is not going too close to the human itself. And we add these objectives into the original aggregation objective and train the control policy by iteratively training a predictive model, which can serve as a reward model or it's kind of a cost function, which gives us the JCP term, and then we iteratively optimize the reward model and the optimization objective to find the best control policy. And this gives us a recipe for a continual learning formulation. You start with a pre-trained policy, you collect some data with it, you train a reward model to score this data, then you train a new policy using the scored data, you collect more data, you score it, you train a policy, and so on. And we deploy this system in our office at Berkeley at the level of the whole floor, where the robot would navigate around doing an inspection task, collect data, learn a reward model, and learn a policy objective. And here's what the learn performance looks like deployed on a robot. Because of some safety constraints, we were not allowed to run the robot faster, so the humans were also forced to walk slower to keep up with the robot. So the robot kind of preempts the plan of the robot, forward or backward, and moves out of the way if it can, or it stops so it doesn't hit the human. And this this is what you would expect as predicted behavior, but this is happening entirely in the image space without any detections of humans. Is another example of what the performance looks like. So when you see when the human is coming, the robot kind of preempts the human's position. It tries to move out of the way, and the human can keep on doing what they do. We have kind of a few more examples in different environments where the robot either stops or moves out of the way to do this. And to measure performance, what we did is this was lying around on the whole floor. The robot was just doing laps and autonomously solving the task. And whenever it either hit something or it was asked by a human to stop, we logged the number of interventions it takes to get this robot running, and then we logged the number of interventions per hour. So over multiple days, you can imagine the policy would improve. And we did see very sharp improvements after 1 to 2 days of deployment. And after about 4 to 5 days of deployment, with continual human-in-the-loop learning, the robot eventually requires the order of 1 intervention every 10 hours, which means you can now have a fleet of these robots and completely let them solve the task in your environment without having to scale up human annotators. And to understand the role of training on all of this autonomous data, as well as the objectives that we talked about, we did a few comparisons. In the interest of time, what I'm going to kind of leave this at is the only way to do real-world human evaluations is to do a user study. So we did a user study with 25 participants in different environments, and we scored likability metrics and smoothness metrics and so on. And we found that the combination of autonomous data collection and using an interesting algorithm to do this that makes humans believe that the robot is better, and they would start working nicer with it. Some interesting findings along the way. We found that when we deploy in different buildings, when we deploy in the CS buildings, for instance, students don't really care for the robots. They'll just ignore. Like I love this video where somebody's just doing their thing and the robot just walks up close to them and they don't even care. But when you do this in a different building where people are not so used with robots, they would just sit around and stack up near the robots. So maybe just inspection is not the right objective, and we need to design a better task so people want to interfere with, to interact with the robots. Another interesting thing, very similar to the motivation for this project, was that the way people react depended strongly on the nature of the policy. So people can easily tell when the robot is running a random policy versus when it's running some very nice learned policies. And we got a lot of comments in our user study pointing out how easy it was to tell the robots apart and how that changed the nature of interactions. So yeah, continual learning with humans in the loop in this way kind of seems inevitable. And that's the kind of key technical parts of the talk. Quick takeaways before we can open up for questions. Real-world robot learning across embodiments is becoming feasible, and you should try it in the cases where this may be applicable for your own problem. Cross-embodiment pre-training is a very powerful tool with almost nothing to lose in terms of performance, but you may gain in terms of generalization and robustness. And online learning in the real world may also be inevitable for a lot of these tasks. So whenever you get a chance, we should think about these. I don't have much time to get into some other related projects that explore the validity of cross-embodiment learning beyond navigation, where we have this large collaboration, understanding how we can do this for other tasks like tabletop and dexterous manipulation and even mobile manipulation, how we can combine these policies with a natural language interface like language models and vision language models for open world instruction following and conditioning with language, and combining them with high-level planning and search-like objectives to deploy these things at the scale of entire cities. I'll stop here. All the papers I talked about, we have the code and models and all the nice things public on the websites if you're interested, or you can also shoot me an email if you have any questions after this. But we can open the room for questions now.
I have a question. Thanks for the great talk, Dhruv.
Go for it.
In the last part, you were talking about interaction with humans, and it seems like the costs that you had added to the function were generally very, I guess, deferential. Like you're just basically trying not to bother the human. Do you have ideas on more general, like cooperative interactions between robots and humans, and what the right framework for this is?
Yeah, that's a great question. This is something I try to touch upon in the motivation. I think doing it right will doing human-robot interaction right can be of varying scales of. You can go all the way to the extreme where you actually track every human, you have behavior models, you have intent prediction, and you want to solve a multi-agent game theoretic problem, which is what you would do in a very critical setting, like let's say the AV setting. I think for the home robot space or for like slow robots doing their thing indoors, that is overkill, or that may be overkill. I think in the balance, there's probably a happy medium where you start with some sort of a model, which is maybe the way humans like being nudged or something like that, and include that in the training objective. But I imagine we would need a little bit more instrumentation to do that.
Makes sense. I also have a kind of different question, which is more lots of hype around LLMs and stuff, and I know you also have some papers touching on their usage. Which application of LLMs do you think is most useful for robotics? So like historically, people use it a lot for like the task framing. People are starting to use it more in the core like planning components. Yeah, what do you think is the power of it?
It's hard to kind of put a pin on it because with every passing month, we see new capabilities with these models. I think there's two that excite me the most. One, which is kind of now commonplace, which is for task planning. I think LLMs for task planning are here to stay. They work really, really well. And because with all of the inference speed constraints, it makes a lot of sense to use them as the highest level kind of slow 1 or 0.5 hertz planner. The other place where I think large models are very relevant is using using the perception models, the VLM kind of models, for open vocabulary reasoning. In the past, as of a couple of years ago, all the vision language research we did was closed vocab, and that was good for solving benchmark tasks with Hauptmann objects. But the moment you want to put things in your personalized spaces or your offices, you need to start reasoning about more open vocabulary things. And I think just using VLMs for open vocabulary detection and maybe even VLMs for planning, that's a very interesting place to use these things. I'm not yet a very big fan of using them for control, but there are some interesting works coming out in terms of reward design or controller design. So yeah, I might change my answer every few months.
Cool. Thanks.
Yes, sure. Go ahead.
I have a couple of quick questions. I'm curious about the choice of offline RL algorithm which you use, and in what setting. Like, for example, did you pre-train a model, then plugged it into SAC, like, or warm started a SAC to use that, or was it like sort of in something like conservative Q learning, which has an online sort of algorithm that was plugged into? So could you maybe cover a little bit more details?
Yeah, I can share more details there. Yes. I think all of them are pretty good choices, and I've used different ones for different use cases. For the research I talked about, we use this algorithm called implicit Q learning, or IQL. The reason IQL is a great choice is IQL is actually very similar to BC in the way it is set up. It is one of the it's one of the easiest changes you can go from goal condition BC, and I think the choice of IQL was purely a convenience because we had BC working very reliably. So IQL was a good framework. And what we did there was we trained everything with IQL, and then for online improvement, we used this algorithm called RedQ, which is another Q learning algorithm. I'm happy to share a link. It's kind of like DRQ with a lot of online updates. So the rough idea there is you want an online algorithm because online data collection is so expensive. You want to have a Q learning algorithm that has a high update to data ratio, or UTD. And RedQ is just really optimized for a very high UTD. In some more kind of recent things, unpublished works, we've also been playing with CQL and this algorithm called CalQL, which is calibrated conservative Q learning something. And I personally don't have a lot of strong intuition about what the benefits are between them. I kind of think of this as a large model class to tap into when needed. But yeah, if you have more follow-up questions, I can answer those too.
Could you just maybe quickly mention that the Q learning algorithm you mentioned?
Yeah, I can send you a link.
Oh, okay, wonderful. And I have a quick question. So did you do any sort of domain adaptation when you were doing sim to real?
No. So first, we never actually did any sim to real. Like there was no simulation training happening anywhere. But there were a lot of like real to real generalization examples, and there was the real to sim generalization examples. There is no explicit domain adaptation step in all the methods I talk about. I think one way to think of domain adaptation here is your pre-training is domain randomization, and your fine-tuning is roughly domain adaptation. So if you go to a new environment, you're deploying zero-shot, it kind of works, but it breaks in some cases. You collect some data, you fine-tune the model with the same objective, and you could count that as domain adaptation. But it's nothing very smart. It's just simple fine-tuning.
Thank you.
Yeah, I see we're at time, but if anyone has questions, I can stay for a little bit longer, or you can also shoot me an email.
Yeah, I think I need to wrap up.
Okay.
First of all, thank you very much for your great talk. Let us
Thanks, Alexander. Thanks everyone for joining.